Okay, so we're going to work through the stone being dragged up a hill problem. And you've got, so looking to stay fit, a person is dragging a large stone up a hill at a constant velocity. So the hill has an incline of 40 degrees. And we've got this stone. And we're told that the mass of the stone is 30 kilograms. So we'll put that up here. Person's pull is 250 newtons and parallel to the incline. And they're dragging it up the hill, so it's going to be this way. Call that FP. And we're told how big that is. We're told that FP is 250 newtons and it's parallel to the incline. And there is friction between the hill and the stone. Okay, so that means that since this thing is traveling up the hill, right, at a constant velocity, then we have some force of friction that's going to be opposing that motion. And then we have the usual stuff. So we have force of gravity downwards. Probably should draw that a little bigger, but it works. And then we have normal force from the hill. And in your written work, draw a free body diagram of the stone. Okay, so we've got all of those things right there. It's not really a free body diagram because it's on the incline, but it gets the point across. And B, what is the coefficient of kinetic friction between the incline and the object? Okay, so if this was kind of A, then B is find this kinetic coefficient of friction. Okay, so first we need to recognize that the way that we're going to get at this is by analyzing the forces, and that namely we need to find the frictional force which will relate to the coefficient of kinetic friction. Okay, so I would set up a coordinate system here so that along the incline maybe upwards is x and perpendicular to it is y. And that way, when we do our sum of forces, we get that the sum of all the forces in the x direction has to be 0 because v is constant, so acceleration is 0. And we have the force of the pull up the incline, we have the force of friction down the incline, and we have also a component, the x component of gravity, also down the incline. And if we're looking at this, we might think, okay, maybe we can get this right away because, I don't know, we have some of this information. But if we start substituting for things in terms of their definitions, or what they are in this case, so mg sine theta, so theta being that, and we don't know a couple of things, right? Well, one thing in particular, which is the normal force along with the thing that we're looking for. So we need to look at the vertical, well, not vertical, but the y-axis perpendicular to the incline. That's also going to be 0. It has no acceleration perpendicular to the incline. And we've got only two forces here that have components components perpendicular to the incline. And that means that F sub n is going to equal the magnitude of the y component of gravity, which is mg cosine theta. And so we can come over to this expression and substitute that in for normal force. And here you can start simplifying things if you want by putting in numbers, if that's nicer for you. I'm going to just do it in symbols because there's a couple of different sets of numbers for this problem, so people can just look at the symbolic version and substitute in their things to check the other version. So we add this to both sides, so we get that. And then we divide everything by mg cosine theta. So we get this expression here. And we know all of these quantities, right? So you have the force of the push, you have 30 kilograms, you have 9.8 meters per second squared, sine of 40 degrees, cosine of 40 degrees, same, okay? So if you plug all of that in, actually, I don't have it here in front of me. Oh, there it is. Okay, I think you get this number, okay? If you're keeping 3 sig figs, which is a reasonable thing to do, but if you just kept a couple, that's fine too. All right, so there's that one, and we'll move on in a little bit.